We're going to be discussing today confidential computing. Specifically, I have the pleasure of having two guests with whom we're going to delve into Intel TDX confidential VMs on Google Cloud. My name is Ijlal Lotfi. I'm the product manager for platform security at Canonical. Jesse?
Yeah, hi, and I'm Jesse Schrader. I'm an Intel principal engineer, and I lead our confidential computing practice. Very excited about what we're bringing to market with Canonical and Google, so happy to be here.
Yeah, hi everyone. My name is Joanna Young. I'm a product manager at Google Cloud for confidential computing, and really looking forward to telling you guys about our products today. So let's start off with abstraction layers. Abstraction layers are a powerful concept. They help us better manage complex systems by breaking them down into manageable pieces. With each layer hiding details of how things work below it, we can bring laser focus to the task at hand and leverage existing interfaces for everything. So in computer science, we make extensive use of this concept, and that's great. So if you're an application developer, you don't have to worry about implementing a CPU schedule, writing your own drivers, creating a memory management system. You just consume these services from the interfaces provided to you by the underlying system. And you get to trust these privileged software layers to manage your application so you can be productive and focus your energy on your project. Unfortunately, this paradigm, as great as it is problematic for data security, because that software that manages your application, all those lower abstraction layers we just talked about, is granted access to your data that belongs to you, and that could be sensitive. Additionally, these lower layers of privileged software have millions of lines of code, millions of lines that could have vulnerabilities while also having access to your data. So when you run in the cloud, you have to accept that, your operating system can read your data, and that if your operating system has an exploitable vulnerability, that your application's data could be compromised, and that the cloud provider's hypervisor could also dump your VM's memory. And all of this does not sound good at all. But honestly, in a multi-tenant public cloud, like, what other options do we have? Like, don't we just have to accept trusting these millions of lines of code of privileged software? Well, the current paradigm is exactly how computer systems were designed and how they've been working for decades. And we shouldn't just accept it and move on. We should, and we need to do better. We need a system where the host, the service provider, and all those typically privileged lower layers of software are not able to access user space. And we need to protect the user application from the host. We need to protect customer data from the host. But you might think, okay, well, I already encrypt my data at rest, so my data is protected. I've got key management going. Unfortunately, data has 3 stages, right? So data can be at rest, data can be in transit, and data can be in use. So yeah, maybe you've encrypted your data at rest with a key management system and HSM, and you've also, encrypted your data in transit with SSL and TLS. But what about that third leg, data in use? When that data is actively being used by the CPU and bits of data are flying through DRAM. How do we protect data in use from memory dumps and other memory attacks, especially when that data is running on layers and layers of privileged cloud providers, hardware and software? So we'd like to introduce a concept to you called confidential computing. It's an industry term. It's used by many hardware vendors, cloud service providers, distros, and it's a security technology specifically designed to protect that third leg, that data in use, through hardware-based trusted execution environments, also called TEEs. And there's really 3 main attributes that make up a TEE that allows you to call it a TEE. That's data confidentiality, data integrity, and code integrity. So what we mean by data confidentiality is that means that your data is inaccessible to unauthorized users, like, cloud insiders on the host side. Data integrity means that none of your data is altered, and code integrity means that none of your code running that data is altered. So now with confidential computing, you can ensure that your data is better protected while in use, even from privileged code like the cloud service provider's hypervisor. And that's the security threat model that confidential computing is proposing. It's a new way of thinking. And confidential computing is a new system where you can run user-land applications without having to trust those lower layers of software, those millions of lines of code that isn't managed or written by you, the application developer. So you really go from needing to trust the whole system to needing to trust less of the system. And so now how do we do this? Well, like I mentioned, it was hardware based. So I'm going to pass it over to Jesse from Intel to take it further.
Okay, great. Thanks, Joanna. Yeah, and it's great to be here. And but some might be asking, like, or wondering, what does this even have to do with Intel? After all, we're a chip company, and we're here talking about the cloud. But there's a truism in security, which is basically that security is only as strong as the layer below it. So, that means that vulnerabilities in those lower layers, like the operating system or down in the low, the hypervisor, or even things like firmware or something like that, could potentially become vectors of attack and get access to the application code and data. So the solution really needs to be rooted in hardware so that potential vulnerabilities or misuse in the software stack can't expose the application's data. And so Intel started with something we called software guard extensions, or Intel SGX. And that allows you to set aside specific code and data to operate outside the control and access of the privileged portions of the system stack, so that they can't become the vector of attack against that application and its data. It's important to understand, though, that this is about more than just confidentiality, there's actually three main silicon primitives. Each one plays a critical role. So, first of all, we isolate the access to a specific process. And that's the only thing that can access that memory, and therefore the processing against that data then the running of that code. Any other process, privileged or not, is not going to be able to access that space. And then this is reinforced with encryption, and the encryption key is actually held by the hardware. So breaching the operating system or the hypervisor or something like that does not actually get you access to even the key that could decrypt that data, because it's actually being encrypted at the hardware level before it's written out to memory. And then the last one is what we call remote attestation. But basically, what this means is verification of this entire environment. We'll talk a little more about that, but essentially making sure that the environment and the workload and everything like that is clean, has not been manipulated in some way. We have to be able to know that it's running correctly in order to trust it. And so now, we Intel started with that Intel SGX, but now we've sort of brought a new and simpler model with something called confidential VMs, which are enabled by with Ubuntu and with GCP, and we call this Intel Trust Domain Extensions, or Intel TDX, and that allows a native VM to run in a protected user space. And that's shielded then by the hardware, from hypervisor, from the host OS, from the other VMs that are running in that space. So be able to know that it's running correctly in order to trust it. And so now, Intel started with that Intel SGX, but now we've sort of brought a new and simpler model with something called confidential VMs, which are enabled by with Ubuntu and with GCP, and we call this Intel Trust Domain Extensions, or Intel TDX, and that allows a native VM to run in a protected user space. And that's shielded then by the hardware, from hypervisor, from the host OS, from the other VMs that are running in that space. So the hypervisor sets up this trust domain, and the VM instance gets opened within that. But then the hypervisor, the host OS, they can't see into it, because the hardware is the thing that's controlling the access to that memory space, that guest user space, and access to the key. As I said, the other primitive is around this idea of verification, and it sort of answers this question: how do I know? In other words, you've told me you've given me something that's secure, something that's protected by the hardware, but how do I know? How do I know that's true as the customer, that this trust domain has been set up correctly and has been offered to me in such a way that the cloud provider and no other processes are going to be able to get access to it? And so that's where this attestation comes in, because it leverages cryptographic verification and produces a signed certificate. And that way you can be sure that what you intended to run is in fact what is running, and that the environment that it's running in is sound. And it can also be used to validate certain critical security workloads wherever they're hosted. So it's not just keeping the data confidential. It can also be used to make sure that even though I'm running something in the cloud or somewhere that I don't have control over, I can verify that the workload is that I intend to run is the one that's been running and hasn't been manipulated in some way. So there's several options or sources for attestation services, and this is a choice for customers as they're deploying their workloads to decide how they want to verify. Of course, cloud providers like GCP provide these attestation services, and that can be a great and convenient way to verify that environment. There's also confidential software vendors that provide, software and services that are supported by confidential computing, and often they provide an attestation service that will verify that environment. Some customers want to build their own. They want that level of control that they can just literally build their own attestation service, collect all of the artifacts from the system themselves, and have full control, and that's available as an option. And then Intel also has an independent trust service, which is neutral and kind of supports multi-cloud, and so that's an option that we offer as well to go along with the core confidential computing primitives that are built into the hardware. And so, just to tell you a little more about how this Intel's trust service works, and this is an option available here, is we call it Intel Tiber Trust Services, and basically it does the validation of the confidential computing trusted execution environment, and actually we will be extending it to also be able to validate other devices, roots of trust, other TEs, etc. So it's going to expand even beyond just those Intel confidential environments. But this is a SaaS service, and one of the advantages of it is it can be used in a multi-cloud or hybrid cloud instance. So you can validate across cloud domains or even into your on-prem, and it provides a consistency across those different attestations so that you have that kind of single pane of glass or single view across all of those spaces. And of course, you don't have to develop it all yourself. It's there as a prepackaged service. So this is a great option to combine with the core capabilities that Canonical and GCP are making available. And of course, that's fully integrated with GCP and Ubuntu in this space. So let me pass it over to Ijlal, and we'll continue.
Thank you, Jesse. So that was a great explanation for Joanna, starting with what is the value proposition, what is the problem that we are trying to address with confidential computing, and we've established that it is securing data in use. And Jesse told us how the great silicon innovation has made it a reality today. So with Intel TDX, which is now offered on Google Cloud with Ubuntu VMs, we are able to leverage silicon hardware innovation to provide very strong security guarantees to the data and code that you care about at the application layer. So once you have the hardware, are we done? And that's it. You have your security guarantees met. I wish I could tell you yes, but it is important to understand that what silicon gives you is a primitive. It gives you a trusted execution environment, a TEE, and that is certainly the core of confidential computing. But a primitive is not necessarily the full solution. A primitive is a building block towards the solution that we want. In this case, we want to go from a trusted execution environment, the way the silicon have imagined it or built it, the way TDX gives us the CE, into a full confidential computing, the way the end users, developers want, imagine it to be deployed to meet their requirements. And this is exactly where the role of the operating system becomes important, because Intel TDX, what it gives you is runtime security. What you have to complement it with is a solution in order to continue securing your data when it is at rest, when it is stored in secondary memory. So with Ubuntu, you can leverage, for example, full disk encryption with TPM-backed protection for your keys. And that is offered out of the box with your confidential VMs if you choose Ubuntu as the guest operating system. You also have to think about complementing your trusted execution environment with Intel TDX with a way that is secure for you to transfer data from whatever endpoint it resides initially into the CVM that is hosted on Google Cloud. And you have to make sure that the endpoints, for example, of the HTTPS connection tree terminates in the meaningful endpoints, the confidential VM and the host environments, for example, the on-prem environments from where it is coming from. Another consideration here that you have to think about is related to attestation. And I'm bringing this picture here to emphasize the layers that are running within the CVM. So you can see here at the most privileged layer, you have the in-guest VM firmware of VMF or TDVF. You have the guest operating system, Ubuntu, and then you have your application with the code and data that you care about. And the ultimate goal of attestation is to tell you or to give you a measurement about the entire, that tells you the status of security about the entire software stack that is loaded within the CVM. That is what you want to be reflected in the attestation. But the silicon TDX in this particular case, the hardware attestation it gives you is a reflection of the initially loaded software within the CVM that is rooted into hardware. And then it is up to you again to think about how to innovate or how to extend those attestation guarantees up the stack for them to reflect as well, besides the initially loaded pieces of software, which usually are the firmware, we need them also to include the operating system and the application. So you can make use of here of VTPM PCRs in order to register the measurements of the early boot software and the OS. You can also have here different options that the operating system presents to you in order to extend these attestation guarantees up the layer all the way up to the applications. For example, you can choose to have some integrity measures all the way up to the root FS. And all of these are services that can be offered by Ubuntu as the operating system of choice for confidential VMs. And now we have spoken so far mostly about VMs, and some sort of virtualization layer is definitely required in order to make use of confidential computing, because at the silicon level, confidential computing, Intel TDX are extensions, architectural extensions to the virtualization layer. But you don't have to deploy a VM in order to make use of confidential computing. You can choose to deploy a confidential container, and there are ways, architectural solutions that you can deploy in order to make this possible. So maybe you will have a thin virtualization layer and in which you run your container, and then you have to think about how, again, to bring this primitive of trusted execution environments into confidential computing. You have to think about how to orchestrate this kind of new type of containers, these confidential containers. And these are all things and problems that we care about at Canonical, and we are very much actively engaged in solving. And then confidential computing is it has been a very important primitive that is pushing us all to think more meaningfully about the security of every little thing that runs within our VMs, our confidential VMs in this specific case. And it's asking us to, it's pushing us to ask questions about the firmware. So what is it? What is this firmware that is running inside of my VM? Is it hardened enough? Is it open source? Do I have reproducibility on it? So these are all questions, again, that the industry is working on, and Canonical and Ubuntu are investing in as well. The last question is, how can you protect the confidential VM from itself? Because so far we have spoken at length about how TDX can protect whatever is within the VM parameter from everything outside of it, even protects the VM from the hypervisor and from the host OS, and that's great. But if you happen to have a vulnerability within the VM, then that's on you. You have to still have robust security strategies to make sure that those vulnerabilities will be patched in time. And that, for example, if you have requirements to meet some regulations like FIPS, that is still on you to make sure that the kernel, for example, for the operating system that runs within your CVM allows you to meet those requirements. So this is where it becomes important not to just have any CVM, but a CVM that is supported by a guest operating system that is capable of allowing you to deploy confidential computing at an enterprise scale. Ubuntu offers you Ubuntu Pro, which is a security, it's a subscription of services that, when used with your confidential VMs, it gives you up to 12 years of stability, basically. So it gives you up to 12 years of security maintenance for all the CVEs that can be found within your CVM. It also allows you to have kernels that are FIPS compliant. It gives you access to landscape, which is Ubuntu's answers to enterprise management. And it allows you to maintain a great level of uptime for your CVM if that is what you require, because it gives you kernel life patch, which allows you to fix critical and high kernel vulnerabilities at runtime without having to immediately reboot your machine. And Ubuntu Pro gives you actually the longest time of the longest reboot window, 13 months for this. So you can go as long as 13 months without having to reboot if that's your plan. And very important to highlight here the element of how is security meets stability for your Ubuntu Pro confidential VMs. If there is, I'm giving here the example of OpenSSL. If we are shipping an Ubuntu with OpenSSL 1.1.1 and it goes out of life before the 12 years security maintenance window that we offer for you, then we are still going to take any patches that are offered on newer OpenSSL versions and backport them into whatever version we have shipped. And this is how we ensure that you have a meaningful 12 years of security maintenance and support for your confidential VM deployments. Having spoken to numerous customers who are using confidential computing, this use case has been coming up frequently as one in which confidential computing makes a lot of sense. We call it here confidential collaborative analytics. Think of it in this particular figure here as four different companies. Each one of them is holding a data set, a unique data set of security sensitive data that belongs to them and only to them. And they do not want, or maybe they cannot share it with each other due to regulatory requirements, but they know that there are use cases for them to collaborate on in which it would make sense to collaborate on and from which they can derive value. For example, you can think of these as hospitals wanting to do joint analytics on some patient's record in order to come up with a better understanding of a disease or to have a better way to develop some drugs. So for these particular use cases, collaboration is very important, but security can prevent it in the worst case or slow it down in the best case, because you have to go through a lengthy process of approvals, where confidential VMs here are truly great, offer a great value proposition, because you can jointly release your data sets to the confidential VM after, of course, you have validated that you trust it, after you have validated the remote attestation token that you would have gotten from the Intel TDX environment that you would have jointly provisioned. And only then, after you trust the environments, only then do you release the data set and you run your joint analytics, and you only get back the results that you all four of you care about without having disclosed your data to either party, and also without having run into the risk of having this data leaking into the platform operator, in this case, the public cloud operator. Joanna has some more concrete examples to illustrate the strength of confidential collaborative analytics using confidential accelerators. So over to you.
Thank you, Ijal. Absolutely. I think the use case that Ijal just presented is extremely enhanced by confidential accelerators. And so what do I mean by confidential accelerators? Well, you definitely need a lot of compute horsepower to compute on data that's sensitive. And so at Google Cloud, we offer confidential VMs that we talked about throughout this presentation. They are powered by the hardware-based Intel TDX that Jesse mentioned. And that, Intel TDX is that confidential computing technology. But what's also really cool is those same CPUs that have the Intel TDX extension, a lot of them have the Intel AMX extension as well, which is a built-in CPU accelerator designed specifically for deep learning training and inference. And so when you build that confidential VM, you can automatically have that Intel AMX enabled with your TDX enabled as well. So secure and performant. Lastly, Google Cloud also offers confidential GPUs, which are built on the NVIDIA H100 Tensor Core GPUs, and those will be coming soon. So let's dive deeper into confidential computing use cases. Ijal mentioned one about those collaborative confidential computations where multiple hospitals don't trust each other. but there are many industries that have already benefited from confidential computing. So I'd say the main ones are typically financial services, healthcare, and anybody with sensitive data, maybe perhaps trying to meet compliance or data privacy regulations. So the first one on the left is Monetago. It's a digital platforms for financial institutions, and they needed to detect duplicate financing fraud while ensuring their customer data is protected and in compliance with local regulations. And so they use confidential computing to ensure that their data is protected and their customers' data is protected. In the middle section, we have AstraZeneca, a global biopharmaceutical company who is dealing constantly with secure patient health data, and they needed to have end-to-end encryption, and confidential computing was solving their problem. Lastly, on the right, we have Matrix Software, which is a telecom charging and billing system. And so they needed that extra data protection for their PII and to meet the data privacy and compliance requirements. So all of these companies chose Google Cloud solutions to build and protect their data.
Yeah, thank you, Joanna. I really love hearing about use cases, and I'm sure the people listening do as well, just because it can inspire everybody to think of use cases in which they also can benefit from confidential computing, and in which they can bring this probably latent, dormant, security-sensitive data that they have and that they are not deriving any insights or business value from, and make use of it actually thanks to confidential computing, without having to worry about compromising on security, privacy, or breaching regulations. If you do have such use case in mind, we're very open to, we'll be very happy to hear about it. Do send us your questions reach out on the contact form on the Canonical Confidential Computing website. Ask us questions. We're also happy to engage at that level of conversation. And I want to share with you all this GitHub repository for the products for collaboration that we have with Intel, specifically for Intel TDX. So we have released just recently in Ubuntu 24.04-Intel, it's an Intel optimized, Intel TDX optimized Ubuntu build that gives you the latest and greatest patches that you require across both the host and guest side. So if you do happen to have hardware for Intel TDX and you want to try to build the whole thing yourself and exercise some of your technical muscles, please do go into our GitHub repository. We provide scripts which make it easy to spin up a confidential VM, as well as do the attestation and make sense of how the token is, what guarantees does it give you. So this is a link to the GitHub repo. We are very responsive there, so please make use of it. For Canonical, for any questions, go to canonical.com/confidential computing. And you can find further resources by scanning this QR code. This brings us to the end of the presentation, but not the end of the webinar. So please, if you still have any questions that you haven't had the chance to ask as we were speaking, please do so now, and we'll read through them and answer them. Thank you, Joanna and Jesse, for joining.
Yeah. So on to the questions. I'm looking here into the ones we've received. And I think I have one for you, Jesse. So the question is about if somebody is to run their workload in a confidential VM, is there a performance degradation that they can expect? And if so, what is the magnitude of that degradation?
Yeah, good question. There's two things to think about. The first is just on the practical compute side. It's going to depend on the workload. It's going to depend on how it accesses memory and the frequency of that and things like that. And also it's going to depend on whether it takes advantage of some of the accelerators like Joanna talked about, like Intel AMX. So there's a lot of factors that go in. I can't just give it a set percentage. But typically, you'll see a compute overhead latency of just a couple percent, right? It's somewhere down in the low single digits, and there's going to be variability there, but that's typically where it's going to be, is low single digits. But the other thing to think about is if we look at a lot of these workloads that are good candidates for confidential computing, many times the alternative solution may have significant workarounds that are being leveraged instead of that, right? For instance, there might be a lot of complex data anonymization or various obfuscation techniques that are being used instead of operating these things in a trusted execution environment. We might be leveraging third parties, and there's a process to pass the data to a third party that's independent. Or we may just not be combining these data sets or leveraging the values out of these data sets and not getting the value out of them at all, right? So there's a kind of an opportunity cost there. So it's important to not just compare, how does my compute run here versus how does it run with confidential computing, but to also look at the business process and what's my overall throughput through my business process. And we often find that confidential computing actually results in a large acceleration of the time for the business process as a whole.
Yeah, that's such a good point. And honestly, even if you do take the comparison of confidential versus non-confidential VMs, the degradation being so small is quite impressive, because we are talking here about encryption at runtime of memory. It's quite impressive, and I think that's the merits of doing a lot of this security stuff at the silicon level. It makes it as fast as it can get.
That's right.
Excellent. So I'm going to combine perhaps the next two questions, because the answer is quite similar to both. So they want to know if confidential computing being good for our security sensitive data, some of the regulations would require FIPS compliance, and if this is something they can get on Ubuntu Confidential VMs. And somebody else are inquiring about their ability to, I think we touched on this briefly, but they're asking about live patch capabilities in order to keep uptime while still being able to patch kernel vulnerabilities without having to reboot and stop whatever they are doing, which I suppose is quite important if you're doing training for some model. You want to keep uptime as much as you can. The answer for both of those would be you want to make use of Ubuntu Pro. So that is still your same Ubuntu image, right? And you just attach a subscription token to it, and that gives you entitlements. One of them is extended security maintenance for 12 years. Another one of them is live patch, and the third one that I will mention here is FIPS kernels. So we already have that available on Ubuntu 22.04, and we are ahead in the process of getting FIPS into Ubuntu 24.04 as well. I think there are also a question about if somebody can talk to the Canonical team about collaboration. If it will make it much easier, Eduard, if you can send your question to the contact form for the confidential computing webpage. This way we have your contacts, and we'll definitely be reaching out to start a conversation. And that's an invitation for everybody else who has a question in mind. Let me look at the other channels for questions. I do not see any more. So this brings us to the end of the webinar. Better in order to learn. Okay. Yeah. Any final words, Jesse or Joanna?
Well, I appreciate the interest. I appreciate those who attended, and certainly there's a lot more information online between all three of our organizations collaborating together on this, and a lot more case studies and examples of how this is being done. There's a lot of open source content out there that can be leveraged, but there are also vendors who can bring in add-on services. So I encourage people to keep digging in and see what can be done.
Then with that, I will say again, thank you to everybody for your time, and we'll see you in another webinar for confidential computing. Many of them are still coming.
Okay.
Cheers, bye-bye.